So here we go on, we've now reached about 1900, and at the end of the 19th century, the end of the 1800s, I guess there was a little bit of people thinking that we pretty much got physics taped, really. I mean, there was a few little loose ends, but basically we knew quite a lot by now. So I'm going to remind us where we've got to, and then we'll go on to new stuff. So where have we got to? Where have we got to at the end of the 19th century? Well, we determined that materials are all constituted of aggregations of tiny little particles called atoms. There are about 90 different types of atom, each representing a different chemical element. They can combine with each other in fixed ratios to form compounds, the particles then being called molecules, and indeed they combine to make all the observed different types of matter. So, although at this stage we haven't quite shown that atoms definitely exist, within a few years of 1900, Einstein published what was felt really to be convincing evidence. So we know about elements and atoms making up everything. We know that gas molecules behave effectively like little billiard balls, rushing around at speeds several hundred miles an hour, bouncing off things, and this idea explains all the known properties of gases. We've discovered that there are two forces in nature that act at a distance. There's gravity, which acts on things' mass, and there's the electric force, which acts on charges. We know that interactions between items moving and colliding with each other are always governed by two completely inviolable laws, the conservation of momentum and the conservation of energy. And we've established that heat is a form of energy. We also have now found that light is a wave of electric and magnetic fields. So there we were at about 1900, and it all looked pretty good. And then it all started getting rather more complicated. Oh dear. But before we get to it being rather more complicated, I'm just going to pause with something where we can sort of clear up some of where we got to. No. Sorry, I seem to be having a bit of trouble with getting Zoom to look sensible. I don't know what's happened to it. I can't get anything sensible out of it. Oh, perhaps that's what I want. Oh, good, right, I'm sorry about that. Oh, and there are various people to enter the waiting room. I shall admit them furiously, including iPhone, whoever iPhone may be. And okay, so if you can see this on your screen now, these are some of the main players in this little bit that I'm going to talk about now, which is getting a bit further with the famous periodic table. So we have Thomson, discovering the electron. Then we have work on the atomic nucleus by Rutherford. Henry Moseley I've put in, who was actually very significant. And I was going to mention him because he's about the only serious scientific alumnus of my very modest little college at Oxford. Sadly, he was killed in the First World War at the age of 27. So it's amazing that he got as far as he did in the time that he'd got. So these are the people that we're now going to be talking about. And so first of all then, what did Thomson discover? Well, we were left last time with this question of charge, that there was this mysterious phenomenon called electric charge, which seemed to flow in metals and seemed to be able to be transferred from one object to another, making one positively charged and one negatively charged. But what is it? Is it a fluid? Is it a gas? Is it a sort of property like heat, vibration? Well, Thomson just finally established that actually the negative charge that we see flowing in wires, and which is presumably rubbed off things when you do, charge something up statically by rubbing one object against another, consists of little tiny particles called electrons. Well, that's what he called them, from the Greek electra, which means amber, I think. So tiny little things about a 2,000th of the mass of a hydrogen atom, but which had a fixed mass and a fixed charge. And that was really just about all you could say about them. That's all there was to them, that they were very small, they had a mass, they had a charge, and they were the things that flowed in metals. It was then discovered that you could actually, if you heated up a piece of metal and put a large voltage across, so if you've got a bit of metal there and you created a hefty voltage between it and a screen here, with good old Volta's batteries, you could actually pull the electrons off the metal plate, particularly if you had a little heater there, and get them going at hefty speeds by virtue of the voltage that they were being accelerated across. And so you could actually get rays of electrons. So this was exciting stuff. And then you could use them to bash into things and see what happened, which is what Moseley did. So that was the first discovery, that there were electrons in solids. Now, quite how they were there was not known, so it was thought that maybe the body of each atom was basically a sort of blob of positive charge with these little tiny electrons dotted in it, rather like raisins in a pudding. In fact, it was known as the plum pudding model, because it looked rather like a sort of Victorian Christmas pudding of a blob of positive with these little tiny dots of negative in it. So that was the first idea. Then a chap called Rutherford decided to try, because radioactivity had also been discovered and certain elements seemed to shoot out strange rays of alpha particles and things. And quite a lot of early physics, of course, is a bit of trying things out, playing with things. What can we do with these? Well, he tried firing them at a thin, very, very thin sheet of gold. And his rather surprising results led him to the conclusion that actually atoms weren't a big blob of positive with little dots of electrons in it. Actually, they had a tiny little blob of positive in the middle and an enormous region. Virtually the whole radius of the atom was nothing except presumably electrons doing something. But the actual so-called nucleus was tiny, really tiny. I mean, we've discovered that the wavelength of light, I pointed out, was about 1,000th of a millimeter. Well, the radius of an atom was about 1,000th of that, and the radius of the nucleus was about 10,000th of that. In fact, I've sort of worked out that if an atom fitted into the nave of St. Andrew's Church, then the nucleus would be, if you can see this little tiny dot, this little seed on a bit of paper, would be that size. So a tiny little poppy seed in the middle of St. Andrew's is what most atoms look like. So that was rather a surprise. But it did, then what old Moseley did was use this new accelerated electron sort of gun arrangement to fire electrons into different elements and see what of this had been discovered to create X-rays. Now, quite how, but they were beginning to have suspicions as to what was going on. And using this experiment and seeing how the frequency of the X-rays that came off varied, he was able to establish that what distinguished the elements was how much positive charge there was in this nucleus. That hydrogen had, if you like, 1 unit of charge. Helium had exactly 2 units of charge. Lithium had exactly 3 units of charge. This was what constituted this is what made elements in the periodic table. So we'll go back to screen sharing and we'll move you on one. And so this periodic table that we've now got, whereas previously this number in the top left-hand side was just the order, sort of rank order of how heavy they were, now that actually means it actually means how much positive charge the nucleus has got. This has got 1 unit's worth, this has got 2, this has got 3, this has got 4, this has got 5. So this at last determined what makes an element. What makes fluorine is having 9 units of charge in its nucleus, and hence 9 electrons tootling around outside. Subsequent to this, it was further identified that actually there are 2 types of particle lurking in this nucleus. There are protons that are the positive charge things and a neutral particle called neutrons. Both of these have pretty much the same mass, which, as I've said before, is about 2,000 times the mass of the electron. These figures underneath here, you can see 1.01, 6.94, that is the atomic mass, which is the number of protons and neutrons. The reason that it's not exact number is that lithium, by looking at this, most of the time consists of 3 protons and 4 neutrons, but you sometimes get atoms of lithium that have got 3 protons and 3 neutrons. So it's either 6 or 7, and looking at that number, most of the time it's 7, but sometimes 6. So these numbers at the bottom represent, if you like, the average total number of protons and neutrons. And this thing is the number of protons, which determines what element it is. Now, we still don't know why there's this funny sort of periodicity, why when you've gone up to 10, you then go back to something which looks rather like 3. And by the time you got to 18, you get something that looks very much like 10 again. We haven't discovered that yet, but we have at least discovered the principle of what makes an element is how many protons it's got. And the mass of the atom is then both the protons and the neutrons. Of course, protons are positively charged and they're terribly crammed together, so they're trying to fly apart. And the only thing that stops them is a new force, the strong nuclear force. Physicists are very imaginative, aren't they? So they decided to call this force the strong nuclear force, which attracts protons and neutrons together at very, very short ranges. So that overcomes the repulsion of the protons. But it is a short range thing. It also tends to mean that as the elements are getting larger and you've got more and more protons in there, it becomes more favorable for the atom to have a bigger number of neutrons to sort of spread the mutually repelling protons apart. So you'll see that by the time, for instance, we get down to uranium, that's 92 protons, but whatever that is, 146 neutrons. So it's got a lot more neutrons than protons up at this big end of the periodic table. And beyond uranium, basically, the repulsion of the protons is too big for the poor old strong nuclear force to cope with. And so the things start falling to pieces. And all of these elements are unstable. And bits of them fly out and they quickly decay to a smaller nucleus. In actual fact, most of these high things, polonium, that was the thing that the poor Russian spy was poisoned with, that's a radioactive. All of these things, the sort of 80s and 90s, get to be radioactive because the proton repulsion is really getting too much for the nucleus, and little things like these famous alpha particles, which consist of 2 protons and 2 neutrons, fly out to get the thing less big and more stable. So we've made quite a good bit of progress with the periodic table. Still a stage to go, but quite a bit of progress with it. Now then, about having issues with the technology. Now then, though, things were beginning to, this is where, if you like, the wheels started to come off in the physics, because there were problems beginning to emerge. If a positive nucleus has got negative electrons around it, why don't they just get attracted into it and fall into it? Well, the thought was maybe they're orbiting around it, like little planets going around the sun. The trouble is, according to the theory of light and electromagnetic radiation, that's just the sort of thing that ought to give off radiation, and it doesn't. So that's not very good. I mentioned before the ultraviolet catastrophe, didn't I? This was something else. Oh, now somebody, I'll let iPhone in, whoever iPhone is, and well.
Oh, we're in. Woo.
Right. Sorry. And we'll move on to the people who are big players in the next part of the game. Ultraviolet catastrophe, I mentioned. Do you remember that when we found that hotter bodies give out radiation at shorter wavelengths, the original theory said that hotter bodies, in fact everything, ought to give out all their radiation at extremely short wavelengths, which doesn't happen. So something's wrong there. Then we have the phenomenon called the photoelectric effect, which I'll talk about, which Albert Einstein again solved that problem in the same year that he solved the atom problem and came up with special relativity. He did all 3 of them in 1905. So he was a bit of a whiz. Then we have Monsieur de Broglie, I don't know how you pronounce him, and Niels Bohr, a Dane. Those are the big players in this quantum physics, which we're going to be talking about now. So, first of all, the ultraviolet catastrophe. What could we do about this? Well, the first step was made by a chap, Max Planck, you may have heard of, who found that the mathematics worked beautifully if you made a rather strange assumption, which was that you couldn't put out any amount of light that you wanted down to the tiniest amount. Light was sort of atomized like material, just as we found that you couldn't get a smaller amount of hydrogen than just one hydrogen atom. You couldn't get a smaller amount of light than a quantum of it. And the quantum's energy turned out to be dependent on its frequency. So the energy turned out to be, this is Planck's constant, so he got a constant named after him, that times the frequency of the light. So the bigger the frequency of the light, the bigger the energy of the smallest little lump of light you could have, the quantum of light. Now, to be honest, quite how he came up with that and why, I don't know. But it basically made the maths work. It meant that it was harder for bodies to emit things with very, very high frequencies, which means very short wavelengths. So that explains why only very hot bodies can emit things with short wavelengths like light, ultraviolet, and so on, and cooler bodies can only emit quanta of lower frequencies, i.e. longer wavelengths, like infrared. Then we had this phenomenon of the photoelectric effect. Now, I mentioned that people had discovered you could pull electrons out of a metal plate by putting a big voltage across it and sucking them out. It was also found that you could get electrons out of a metal plate by shining light at it. This was known as the photoelectric effect. But the way in which the details of that, though, were very peculiar. I mean, if you imagine the metal, for now, is a beach of pebbles and the light coming in is the waves of the sea coming in, you'd think that the bigger the waves, in other words, the brighter the light, the more the poor little bits of shingle will be chucked around, wouldn't you? But it turned out that the brightness of the light made absolutely no difference at all. If you had too much distance between the waves, i.e. too long a wavelength, you didn't get any electrons chucked out of the metal at all, not a sausage, however bright it was. But if you increased the frequency of the wave, reduced its wavelength, so waves closer together, you did start getting pebbles fly out. But the strange thing again was that even if you had a very, very small wave, instead of moving lots of shingle a little, it moved one stone would fly out. It was much more as if there was somebody in a boat shooting at individual pebbles than a gentle wave washing into them. Very odd. And so Einstein came up and said, well, basically, Planck's sort of quantum of light energy actually is a little particle. It is a little lump of light. And when you've got not much light, you haven't got many of these little lumps. But each lump, if it hits an electron with enough energy to chuck it out, it'll chuck out. So you get one or two pebbles flying out with a dim light. And as you brighten it up, so more little quanta of light are arriving, you get more stones flying out. But essentially, the light acts like a little particle. In fact, it was called a photon, from the Greek for light, a photon of energy, light energy. So, in other words, we have this mysterious phenomenon that a light manages to be both a particle and a wave, sort of, at the same time. How on earth does that work? Well, to be honest, we don't know, do we? But this is where quantum physics starts becoming rather weird. All a sort of general principle seems to be that if things at the spotlight, sorry, the higher the energy, in other words, the shorter the wavelength, the higher the frequency, the more particle-like the behavior of light seems to be. So these gamma rays are really just like particles. You can't really detect any wave-like characteristics of those. Equally, radio waves are really all about waves. There's really no aspect of them in sort of everyday life that reveals a particle-like behavior. But round about here, the visible band and the ultraviolet and X-rays, you are able to see both. You see the sort of the interference phenomena that we talked about with young slits, the fact that light going through two slits interferes to give a pattern of light and dark spaces on a screen. You get the same sort of thing with X-rays and ultraviolet light, but equally ultraviolet and X-rays also display distinctly particle-like behavior. Ultraviolet light is the thing that gets the photoelectric effect going really well. And so there, it's very obvious that what's hitting the screen, or what's the metal screen and kicking the electrons out, are like little bullets, little particles. So that's where we are now. And then something else, even weirder in a way, emerges. So now I'm going to have to play around with a new, I'm sorry, there's still some sort of squeaking. Could I ask everybody to mute themselves so that we don't get weird sort of squeaks and squawks coming in? Now then. Oh yes, okay. Right, I'll see if I can get this bit going. Share screen. That. Share sound. Let's hope this is going to work.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Right. So, I hope you managed to see that all right. So there we are then. What's an electron? We don't know, do we? All we can say is that it has characteristics of a particle. It has mass, it has charge, it has a wavelength depending on how much energy it has, using that same principle that we've had before. And there's one other strange quantum property it's got, which is referred to as its spin. Now that again, it's not really spinning. There isn't anything there to spin, but one of the characteristics, or one of the ways this manifests itself, reminded people of a sort of spinning electric charge. So that's what it was called. But all I can say is there is a sense in which an electron has a sort of direction, that there is a difference between an electron sort of pointing up and pointing down. There are only 2 ways it can be, but it can be in one of 2 situations in any particular circumstance: spin up or spin down. Now it all sounds a bit woofly, but really those things, the spin, the charge, and the mass, are just about all there is to know about an electron. And what actually it is obscure. Now, we'll come on to a final sort of discussion in a moment, but I just want to indicate how this does help our understanding of the atom and the periodic table. Because electrons, when they're around a nucleus, are something like this. They're not whizzing around at great speed, attracted by large voltages or anything like that, which is how we always observe them when they're actually in free space, because you've pulled them out of things and they're whacking along at great speed because you've accelerated them. So they tend to look very particle-like in that situation, but round an atom, they are not high energy. And so applying our principle of the particle-like features are most obvious at high energies, and the wave-like features are most obvious at low energies. Round an atom, the electron is really mostly sort of wave-like. And you may remember when we talked about waves and sound, and I said that when a wave is confined in a thing like a tube or a box or an organ pipe, the only wave that really works is something that fits in neatly, whose wavelength is of the same as the size of the box. Well, the same sort of thing applies here. If you can imagine, I mean, it's very crude, but if you imagine a sort of wave going round, sort of like that, that's meant to be, do you see what I mean? That it's sort of high here and then it goes down low there and then comes out. If it has one complete wavelength in this space, that fits in so that electron can survive there, but only with the particular energy given by that wavelength. So an electron can be like that. And then because of this funny spin business, you can have another electron also in that same sort of situation with its spin the other way. Because a final strange feature of these electrons is that you can't have two of them in exactly the same state. You couldn't have, if you've got one in this one wavelength situation with its spin up, and then you've got another one in that same one wavelength situation with its spin down, that is it. You can't cram another electron into that state. So supposing you've got 3 protons here, so you need to have 3 electrons. Well, okay, the next one has to go into a situation where you've got 2 wavelengths round here. So I'll try and draw that. But basically, you've now got 2 wavelengths in the confined space. So you can have one in that situation, and we can have another with a spin down. It turns out that as it's getting more complicated with 2 waves in the space, you can also have it orientated different ways. So there are actually 6 different ways in which you can cope with that. So this begins to explain at last why the periodic table looks like it does. If I go on to this again, share and back, that hydrogen has got 1 electron in its 1 wavelength shell, so-called. Helium has got 2, and that fills it up. So the next one has to have 2 electrons in its 1 wavelength shell and 1 in the beginnings of the 2 wavelength shell. And this lot goes across filling up the 2 wavelength shell until you filled it up completely. And that's this neon. Then you start on the next one. Now these wretched little shells overlap each other a bit, but effectively that's the principle, that you fill up the ones that the lowest energy ones that you can, but when you fill them up, you have to start on the next slot. And therefore, what makes the elements behave differently is how many electrons they've got and their configurations. So, for instance, something like, now I'm not a chemist, so I have to sort of dodge about this, but I think something like sodium, you see, it's got 2 electrons in there, and then it's got 8 in this next bit, and then just 1 tootling around on the outside. Whereas chlorine has got 2 in the first lot, 8 in the next, the 2 wavelength lot, and then it's got 7 round here. So it's, if you like, got a hole which could quite neatly accommodate 1 electron, whereas sodium has got 1 that's in a higher energy state than everything else and feels a bit lonely. And effectively, this would love to snatch that electron, and this would love to get rid of that electron. So they join together very happily to make salt, and it's actually very difficult to get them apart again. So that's, if you like, a sort of very simple introduction, but that is sort of why the periodic table works like it does. Elements are defined by the number of protons they've got. The number of protons determines how many electrons you've got, and this strange business of electrons behaving like waves at low energies, and hence meaning you could only fit particular wavelengths in, determines the situations that the electrons find themselves, and hence you have metals which have a few surplus electrons tickling around on the outside, which the thing would like to get rid of, and you have reactive non-metals with gaps out here which would like to suck electrons in. So that is at least one thing that this quantum theory does help to explain. But I think I will just liven us all up now by first of all saying that I think Niels Bohr was one of the people who said at the beginning that if anybody who isn't really shocked by quantum theory the first time they've heard about it can't possibly have understood it. You know, it's peculiar in extreme. Just to finish up with, this is the standard model of particle physics. Now, obviously, this is really a bit OTT. Oh no, where has my Zoom thing gone? Oh gosh. No, come on, let's. Oh, are you still sharing? No, you aren't sharing, are you? Right, sorry. Right, here we are. So what on earth's all this garbage about? Well, I don't really want to go into too much detail, but it turns out that actually protons and neutrons are made out of things called quarks. The up and the down quark. Wonderful names, aren't they? The proton has got two ups and a down. The neutron, a dud, has got two downs and an up. And all the matter that there is in the universe is really constructed out of these things: up and down quarks that make protons and neutrons, electrons tootling around the outside. What's this strange little thing? Well, a strange little thing. What are these? These seem to be simply heavier versions of these. And this lot is a heavier lot again. What are they there for? Because you don't find them in nature. The only way you get them is by slamming things into each other in the Large Hadron Collider and observing what comes out and doing lots of clever maths. What are these two generations for? Don't know. They just seem to be there. Why? Don't know. Why do these neutrinos exist? Well, it's something to do with another strange, the fourth force that we've discovered, the so-called imaginative weak nuclear force, which allows these things to change into each other and gives these out. But it's all rather strange. And I think all that I really wanted to emphasize is that really why these things are around, we don't know. What are these? These are the particles associated with the forces. This is the particle, the photon of light, which is associated with the electric force. This is the gluon, yes, is the particle associated with the strong nuclear force. These two are associated with this weak nuclear force. What does that mean by having these particles? Well, the wonderful way it's put is that the electric field or the strong nuclear field consists of the exchange of virtual particles, the exchange of a virtual photon. What on earth is a virtual photon? So all I think was I was wanting to get across by this is that it is all very weird. And actually, I think it's a bit, we don't really understand it. And although we can do maths, which works very well, what on earth's actually going on is quite obscure. And this is where I just wanted to get onto the little sort of reflection at the end, because I've actually found this quite interestingly and helpful, really, with regard to the jolly old Christian faith, because there are aspects of that that sound impossible. You hear that Jesus, the Son of God, was both fully God and fully man. And you might argue, as indeed I've just read a couple of books by learned theologians, that he can't be both God and man, because if he's fully God, then he can't be man. And if he's fully man, he can't be God, can he? So that's obviously silly. So obviously he wasn't really. He was obviously just a good teacher, and that would be much simpler, wouldn't it? But of course, if one's been exposed to quantum physics where it can't be a particle and a wave, that's silly. If it's a wave, it can't be a particle, and if it's a particle, it can't be a wave, can it? Well, but nature says, well, I don't care, but it is, and you can like it or lump it. So in a way, it gets one used to the idea that things in the sort of real world are a bit weird. In fact, maybe beyond the powers of our poor little brains to grasp completely. We've made remarkable progress, but if something seems a bit paradoxical, like the Trinity being 3 in 1 or 1 in 3, or Jesus being both God and man, I suggest that that isn't evidence of it being a silly nonsense. If it was all beautifully logical and clear and simple, that would be pretty good evidence that we'd made it up. But if it seems a bit strange and baffling, and how on earth can it be if you're either 3 or you're 1? You're not both. Well, actually, there are examples in quantum mechanics of it actually things being 3 in 1, but I won't go into that now. But I think that was the interesting little parallel that struck me, that nature seems to be paradoxical when you really get down to the depths of it. And so perhaps if what we appear to have sort of found over the centuries about the nature of God can only be expressed in sort of paradoxes, well, I feel that suggests that perhaps one's on the right lines then. So interesting stuff, eh? Right, you'll be relieved to hear that is the end of that. And I suspect many of you are feeling completely banjaxed. Now, I'm not sharing screen anymore, am I? I'll stop recording. Yes, I